what I will share is some thoughts about the topic that many has been discussing lately, but many of the questions have been answered by seismic. You know, before the widespread use of good quality PSTM, the basal salt was everything that we could see with luck, not only in the South Atlantic but also on the Conjugate margin of Africa. And over there what you have already, and most of the seismic I will show, it has no interpretation just on the sides, because I think it's, you know, those who cover everything with a little, you know, transparent color, you know, maybe we're not sure about the interpretation anyway. But the point is that here you have the base of salt somewhere, you have those windows, and most of the source rock from Brazil is coming from the rift or also from the lower part of the sag, you know, and we will define those terms, so we are in agreement, and goes through and has fed all the post-salt traditional fields in Brazil, from Roncador, Merlim, all the turbidites, what made actually Brazil a big producer offshore, Campos and Santos particularly. And has been always the dilemma whether below the salt we have only the source, but or the other elements of the play. And only when PSTM came in to our help, we realized that, first of all, obviously, we knew that we have for any trap under the salt, we have a good regional top seal. We have the source, and then what we were missing, and now we know that we have, is a series of reservoirs among which carbonates stand out. But also today I will refer to the influence of this half-graben that I think is very clear here. You know, the half-graben goes this way and has a ramp area, you know, margin, you know, and goes here, and you can see even the fault plane reflection that actually shows where the fault, the master fault of this asymmetric half-graben, and then it comes out. So the theme of this talk is just to take a look at this portion and see how the influence on reservoir, on the location of the key reservoirs, but more importantly, on the configuration of the trap and different trap geometries. So I think I can go this way. So obviously I should start with Tupi. You know, Tupi is the major discovery, the game opener for the play in Brazil. And as I said, the influence on location of reservoirs, and the reservoirs are listed here in this kind of prism that goes in light blue, which is the sag. And here we have, as we saw there, you know, in the previous slide, we have the half-graben. So, and all this is our salt. Most of the discoveries before the pre-salt became a play were coming from all this section, from immediately above salt, carbonates, and then turbidites above. So right now, what you just saw is in this area, Santos. So the pre-salt expanded to Campos. Campos had always a couple of discoveries, all discoveries in the pre-salt in the close to land, a different, more kind of rift play. You know, the one we are talking now here is the sag section. And now we will see the challenge is how to extend from this ridge the same concepts, or some of those concepts, to the south. You know, so you have the entire Pelotas Basin, then we go to the Punta del Este Basin, you know, and you go all the way to the Falkland Islands, you know. And one of the challenges that many explorationists had is that, okay, from the Walvis Ridge, or from this, let's say from this ridge down south, there was no source rock, you know, and we will see that that has been partially answered, but sea lion discovery here in this area north of the Falklands. So one of the elements, and it's a synrift trap, one of the elements seems to be okay. So all this started, and again, we're looking at the southernmost part of the South Atlantic. As you know, the South Atlantic opened in a diachronous format, you know, with the pivot somewhere off this map, I would say here. And imagine this is like, you know, opening this way, and the South Atlantic is obviously in marine domain first, and then the Walvis Ridge, and this ridge that I mentioned here divides two areas. This area here, where Campos, Santos, Espirito Santo, and the Conjugate margins. The most popular now is the Kwanza Basin in offshore Angola, where they're duplicating in a mirror image type of style the discoveries of the pre-salt right now, especially our colleagues from Cobalt, you know. And then what you have is a major paleogeographic barrier that separates this evaporitic basin, you know, from this kind of more open marine basin or series of basins. So in a sketch, what you have is a mirror image, and as I said, you know, and this is a nice sketch that I think it will set the context. What you have here in light blue, in this kind of PR pitch, you know, is the discoveries that are always culminations around some kind of topography inherited from the half-grabens, you know. And when we go here, and the play openers, the Camellas and Biquar, you know, and Orca, and all those discoveries by Cobalt recent in offshore Angola, they have the same theme. These drapes that you have here, which is the sac carbonates, are essentially related to these highs. And we will take a look at the detail of how the polarity of those half-grabens have impact on that. But first of all, why you have the carbonates there? And I will briefly discuss the reservoir story. The reservoir story is rather long, and basically what the challenge is to have, for the industry, is to have long-term tests of those sac carbonates, because without that we don't know the decline, and we cannot really say how they will produce. So the industry, in one side or the other, is looking at those long-term tests in order to sanction projects and then start developing things. So the area, stratigraphically, we are concentrated everything below the salt. And here you have the salt, and below you have the half-graben component, the clastic component, closer to the coast is more dominant. And then when you go toward the more distant half-grabens and overlying sacs, the carbonates come in. So we will take a look why the carbonates are there. But first of all, the configuration that I mentioned, that I said it was jumping, kind of skipping pelotas, which is that basin that is between Santos to the north and Punta del Este to the south. Now we are already in Uruguay, for those who know the maritime international borders, you know, but essentially the geology keeps going. And when you start seeing, you know, you start seeing here the half-grabens, you know, and something that is not very clear, that is kind of overlapping on that, you know, and obviously closer to the coast, you know, those the size of those half-grabens are smaller and smaller, but they're there, which is important. So in terms of partial analogs, we have a configuration that is interesting. Another thing that we'll get back later on this talk is the divergence of these rifts. In this particular case, and when you flatten, you know, but even in the non-flattened version, you know, present day, what you can see here is there is a divergence, you know, against of it towards, you know, the coast, you know. Someone will say, okay, are these half-grabens with the divergence or the other way around? Intuitively, normally what you have is an extension here and a ramp, an extension and a ramp. These guys are opposite, you know. So we'll get back why they're opposite, you know. That was a seismic which was kind of okay, you know. Now we go to seismic that is much better, and again we're going to jump back and forth along the South Atlantic. Now we are in Campos, which is the basin that is north of Santos. And when you look here, is essentially what I show in the first slide is this small half-graben. You know, and by simple definitions, we can define, and we're going to zoom in here, and I want to draw your attention to this part. So you have the basement with highs, you know, mostly volcanic. You have the half-graben, and that sequence that by definition spills over and keeps going over the shoulders of the half-grabens is the sag. That is the definition of a sag. So operative, you know, in an operative way, what we define is, okay, you have the synrift related to laterally confined tectonic subsidence, related to the displacement of this master fault, and then we have the sag. And when you have a hint already about something that is crucial to understand these structures, which is differential compaction. You know, you can think about all this being basement, and the equivalent thickness here in the apex, in this particular, the deepest part of the rift, is all sediment. So you keep piling sediment, and that differential compaction, you know, will create some very interesting structures that we will discuss. In summary, what you have is all the plays that you can think of, and there may be others, you know, in the pre-salt. That applies to Brazil, applies partially to Uruguay because we don't have the top seal, which is the vaporate, and clearly applies to many parts of South Atlantic on the African margin. So all this transparent section, and you can see clearly the fanning, is showing that probably you have a source rock here, one of the source rocks, and against the master fault where you have the major subsidence. Here you have what everybody defines, whether it's here on the Tanganyika Lake, it doesn't matter. It's always the same asymmetric rift. You have a ramp, you have the master fault, and then you have the sag, clearly defined, you know, here, and it keeps going. And then you have the basal salt that is in purple, but I don't think you can see it, but it's just there. Okay? So, Tupi, for those who are familiar with that, and we'll see another size, it's just basically a well here, where you have very little accommodation compared to this area, where, and that applies to the reef, and applies partially to the sag, because you still have differential compaction. So, it was, the relief was not as abrupt as during the rift, but obviously there was a bathymetric high around the underlying shoulder of the rift. So here is where most of these four ways that we're going to take a look at, those are the discoveries in Brazil. And by the way, they need to be four-way closures. And we'll get back to that. You know, the four-way closure goes like that. So what people with poor seismic was doing a long time ago, it was good. They were mapping the base of the salt equal to the top of the sag. And that was the only thing, assuming, in a way, I would say intuition played a role there, you know, that we have some kind of differential compaction. So these are the Tupi and others. In this area here, these are the Pampo and other fields, traditional fields close in the rift section. And it's also, when you change the polarity, is the Sea Lion discovery by Rockhofer north of the Falkland Islands, which actually, independent of the size and some speculation in the stock market, what is important is that the source rock is there. So now we're jumping to a source rock that is north of Falkland. We have the half-grabens, we have the source, at least one of the source. We were talking with Craig earlier before this talk that our suspicions of having another source in the lower part of the sag are starting to be confirmed. Okay? So now we're going to see a little bit the influence on the site of reservoir rocks. You know, these famous sag carbonates, you know, they're there. Okay, again, we're using essentially a model that whether you can use it for the Triassic, Newark, in offshore, you know, the US, or you use the traditional East Africa rift system, is always the same. So this area here will have very little accommodation and will have very little clastic input, as opposed to a major relief with fan deltas and associated systems for the rift. The sag will still have some bathymetry, and here you will have, as we define it, a sag coming over this height. Now let's take a look where we have carbonates today in a rift. So what you have here is in the middle of Africa, you know, Lake Tanganyika. This is the master fault. So this is the master fault side of this asymmetric graben that is now filled by a lake. And then you have the flexural margin or the ramp. So let's take a look at these two places, A and B. You know, B indicates where you have beach rock, you know, and calcite cemented ridges. What it's telling to the sedimentologists, to all of us, is that there is no much development of clastic input. So we have the first condition to have carbonates. Let's go to A, also with these crosses that you see here. So those are microbial rifts today. Today, on the ramp of the Lake Tanganyika, at the rift level, you have microbial rifts being formed. On the other side, that is quite a relief, you have basically fan deltas coming from this relief, and you have a lot of clastic input. No way carbonates can survive that by, obviously by clastic input, and they kill everything. So let's take a look at a detail about that, you know, and this is work, pioneer work by some French authors, you know, and you have a sonation, you know, in terms of carbonate facies. And look at this, you know, the microbial rifts, they're here. So just to tell that that is for the rift level. When you go to the sag level, you still have that as a bathymetric height, subdued, but it's still a bathymetric height. So as long as you have that and you are in the photic zone, you know, these guys will survive. Okay? So that explains partially, yeah, you have cockiness, and obviously when you have a delta coming in, clastic dilution, the rift disappears, so it jumps to an area which is actually sheltered from clastic input. So at the rift level, you know, and going into the sag, we have a location that is a primary location for carbonates. And that explains at a sub-regional, even at the prospect level, the carbonates. Then we go into all the discussion about how those microbial limestones work in terms of porosity, secondary porosity, and again, you know, how they can deliver. But just to draw your attention to this fact that on the sedimentation side, the shoulders are very important. Now, so what you have here is this fanning, you know, even though with good seismic, you know, you have the fanning here, and you know, obviously, that this is an area where there was a shoulder, a rift shoulder, and now this is all pinching out onto this height. This is the sag level that is doing on-lap on here. And that is, and it comes back with more accommodation space on the other side. So what people were mapping actually when they discovered 2P was the basal salt. And when you do the basal salt, you do the map, it gives you a four-way closure. It's asymmetric, but it's a four-way closure. And that is, by the way, where 2P was drilled, 2P1. So you can see it better in the detail, you know. This is the lower part of the sag, this is the upper part of the sag, and they went there. Why they went on the flank? Obviously, they were afraid of a ball high issue, you know, and not having any reservoir at the crest. This is just for those who love rocks, you know, and you have salt, you know, which I guess is everybody, you know, and then you have always the microbiolites or the microbial rift, and then you have the coccinea. The coccineas are already, in terms of the positional system, they're already in the rift. So it's not coincidence that you have the rift with the coccineas, like we saw in Tanganyika, and then we have, when the sea invades, you still have a bathymetric high, you know, in the sea, in the bottom of the sea, and that's where these microbial limestones come in. And again, they're dependent on the photic zone. You know, you have turbidity, No way. You need to be in certain depth. This is what it looks like, you know, and those are the reservoirs that will probably put Brazil as a superpower in terms of oil production in the next 5 years. This is the reason why Petrobras is getting back, retreating to Brazil and trying to invest in Brazil. This is part of the same. You use some domo stuff, you know. This is just to give you an idea where this is Campos. You know, the previous one was Santos. So now, let's go back. So we visit briefly because I thought it was a good idea. It was not part of the original talk, but I think it was good for you guys to understand that there is a dual control. Not only the reservoir at that semi-regional basis or scale, but now let's take a look at the influence on the geometries of the synrift and the sag, which I think is very important for when we map these structures. And again, I remind you that you see the pinch out, but basically these are four-way closures, you know, and that's what you normally map. And you're going to say, what the hell is this? You know, this has nothing to do. Well, take a look, because we will, at the end of the day, all these traps are equivalent to a football trap, what we call a football trap. Whether it's a four-way or a three-way with a combination, but essentially four ways. So what I highlight here is the importance of this concept, which is compaction synclines, which I mentioned at least 3 times already, you know, and it is also related to the amount of displacement. When the displacement of this fault, this normal fault, which is the master fault of the rift, is the largest, you have the differential compaction is the biggest. And when it goes, you tip toward the tip of the faults, obviously the compaction will be less. So here you see the master fault. This is and this is obviously one segment. It has a unimodal distribution of displacement along the fault, and that is a proof that is only one segment. And then we have clearly this vertical axis that defines synclines, you know, and this vertical axis of this syncline, you know, coincides with the cutoff of the fault. And sometimes when you don't know where the fault is, if you can identify the compaction syncline, boom, that is where the master fault will be. And you see that the effect, obviously, of the compaction syncline, of the differential compaction, you know, is not that important toward the tips. So this is the way it works in many places, and inspired by where probably were first described, which was the North Sea, and you will see a line that and a line here and a line from Brazil, and you will see how much we improve in terms of seismic acquisition and imaging. Here's how it works. At the rift level, you know, you have the sea. Obviously there is no overburden, therefore there is no compaction. And you start adding, let's say at this point you are with the sag. That is your sag, you know. The sag maybe, you know, there is some bathymetric height here, so probably, as we saw in the seismic, you know, there is a thinning here and there is a thickening here, but it's not as drastic as in the rift, obviously. So it keeps going, and by the way, you have the salt, and then you have probably you are already in the Cretaceous, in the tertiary and in the passive margin, and this is the attenuated, you know, version, you know, when you go up, obviously, you know, of the compaction. But you see that the compaction affects not only the synrift, but everything above. And it attenuates to a point where for this green layer, you know, the differential compaction is not working anymore, and the whole thing is subsiding, and there's no differential compaction. So compaction above normal faults, and that's what we see. And the B is kind of disturbing. But the first one, okay, we saw the vertical syncline axial plane. you know, above the hanging wall cutoff, you know, and this is from, in this case, it's from offshore Libya, certain basin. And then also there is another, it's not so distinct. It's an inclined but less distinct anticlinal axial plane above the footwall cutoff of the basement. And this is trouble for interpreters. And you will see, because it will create an anticline, you know. And if everybody was okay, I guess, so far, with the syncline. With the anticline, we have problems, because someone will come and say, hey, there is an inversion, clearly, you know. How many times we heard that, you know? Oh, it's the Andes for Brazil, and you know, it's the inversion that propagates through the entire continent and inverts some of these structures. I'm not sure about that. Anyway, this is numerical modeling, you know. I will not bother you with this, you know, but essentially, you know, you can go, is the same as Scuccia, is an excellent paper, you know. And the way you progress through the compaction and you start creating, you see here, start creating the anticline that is not very distinct, but it happens, and when it happens it creates issues. And then you have the syncline, which is very distinct. This is the detail, you know, and basically you have again compaction anticline with the syncline here. So, does inversion exist on half-grabens? Of course. I'm not saying that doesn't exist. It doesn't exist in the passive margin side, but obviously it exists. And this, I brought this in, so otherwise they will say, well, Oscar said that inversion doesn't exist, you know, but it does. And this is a perfect example on the Andes. Doesn't need to go very far. You know, the Andes, you have a wonderful half-graben, Triassic age. You have everything. You have the source, you have the reservoir, produce already a billion barrels of waxy oil because it's lacustrine, you know, and then it was partially inverted. And you can see the fanning here. I mean, this is today, obviously, and this is when you flatten it to the base of tertiary, and you see clearly the fanning. You can put here somewhere the master fault, the normal master fault, that has been reactivated during the Andean orogeny, Miocene onwards, racing, you know, and it gives you that, and then peneplain. So it does exist, but I don't think it is the case in the passive margin. This is just of a historical perspective. This is probably the first description in the North Sea of compaction syncline. You know, I salute them because it was not that easy. And they put compaction syncline, you know, sediment on basement. So they have the concept. From that to this, there is a big difference, you know. And why is that important everywhere, the compaction syncline? This is, again, offshore Libya, you know, and we will get back to here. Here we have clearly some very good news for the oil industry. We have a nice carbonate buildup, you know. We have a high, but take a look at this line, regional line, you know. Obviously, you have the detail, you have here the location of strike and deep. Now we're looking at the deep, and then the regional line here also on the deep sense. But look at this sector here. There is clearly a half-graben that has been accentuated, you know, by the compaction. And probably this prospect didn't need that in order to create a four-way closure. But there are others who will need it. And the polarity of the half-graben toward is facing the continent or the other way around is critical. And we'll touch base on that later. So there are alternative models. Someone will say, well, we have drag, normal drag, reverse drag, you know, we have folding over convex fold bends, and this is interesting, and this is the work by John Soppy that we all know, but requires a convex, a Listric fold that we decompose in two elements, usually, you know, to do all this balancing in extensional regimes. So this is another says extensional force folding, inversion that we touch. This is important because we have not seen, in many cases here, in any case, Listric folding, you know, and that's another thing that probably challenges some people. And this is the work by Brazilians, Araujo, you know, a great guy, you know. But and this is a model. It's the classic model, you know, a SOPI, you know, applied to the passive margin. The problem, and we will see that there are some seismic issues as well, you know. The problem is this doesn't exist. We don't see it. We see up to here, and here we see the syncline. So you see how different it is. This is the famous rollover, you know, the work by Suppi and students, you know, and it's valid as long as you have this geometry or this geometry. And then this here, if you have the Listric fault decomposed into linear features, you will have something similar to a compaction syncline. Now, let's move on here. What is the, let's park for a second the compaction synclines. What is the polarity of this half-grabens? Is one way, is opening, you know, in a mirror image way, you know, extension more on one side, so the divergence is always on one side and not on the other? Not really. And this is from a paper in the memoir of the APG, and clearly you see a high, which is like a high, like a first scale. This is coming from this line, again PSTM, thanks to TGS. And here the only thing I highlighted is the basal salt. I didn't want to just mess around with anything. Just you can see. Now here, I'm not sure what it is, but I think it's a compaction syncline. So I think that the master fault for the half-graben, underlying half-graben of this transparent part, which is the sag, you know, is here. So you have the compaction syncline and the cutoff here. I put the fault here. I don't see it. I don't have fault plane reflection, but I know that the fault will be there. And then naturally there is another, from the sequence stratigraphic point of view, on the seismic sequence point of view, there is a fanning, clearly a fanning, and then convergence toward that side. There is less accommodation there. That is the ramp of the half-graben that control also at this scale the position of the carbonates in the overlying sag. Now this fellow goes this way. The coast is on this side, you know. Here is our half-graben. When you go on the other side, and probably here you can see it, you see, probably not very well, but you see here the fanning. Here is the base of the sag onlapping here. This fellow is the other way around. So the divergence is opposite. And that shouldn't surprise us. When we go back to Tanganyika and the work by Rosendahl, you must remember all this, you know, the probe work and all that. It was all there. When you go today to Tanganyika, you will see, or the East Africa risk system, you see there are conjugate, you know, overlapping 100%, overlapping partially, but it's very common to have flip-flopping verges. And you see that all around in offshore Brazil. This is the case I was referring to, Lake Tanganyika. You know, you start, there are subsidiary faults, but this is essentially a master fault with minor subsidiary faults, but the fault, the master fault of this half-graben is this way. And here you have it opposite. So you can have both. In this particular case, you have it here. Yeah? This is the same scale, not the vertical scale, the horizontal scale between the East African rift system and Campos. Exactly the same horizontal scale, obviously exaggerated vertically much more in the East African rift system. Again, and this is the last one. In this particular case, again, compaction syncline, there is a nice high there. For the sag, you may have the carbonates, you may have also rift coquinus, you have the master fault here, there is a high, and then boom, comes back, divergence, you know, whether a sequence stratigrapher or a structural geologist is looking at that, they will both coincide, excuse me, that you have the master fault here, and a half-graben here. So remember the Punta del Este one, that it was virgin this way, and many, you have seen many virgin the other way around in seismic also. So someone will say, that's very nice, but it can be explained by something else. If you give me a Listric fault, I can show you something similar to compaction syncline. Well, I think Davidson and Underhill just in this volume of the APG summarize what we all knew for a long time, and it's an excellent description. And basically I will quote, there seems to be an inconsistency between neotectonic observations and the existence of Listric faults. The curvature and progressively shallow dip in the fault on seismic section was removed when velocity models were applied and they were depth converted. So what happened with all those Listric faults? Most of them disappeared. You don't have the Listric fault, you don't have the other major reason that can account for it, the compaction. And when you see here, I don't see any major Listric case. The quality of the seismic in general in offshore Uruguay is not that good. Even though they have the benefit of not having the salt in terms of seismic acquisition, but they have the problem that they have the top seal. But here is the same seismic that you see, and I will introduce the final concept that I want to share with you, is that why a half-graben with this vergence helps the four-way closures more than the rift with the opposite vergence. And here you have a classic case, of a high, a master fault, kind of resolved in two faults, but or a fault system, and the ramp. And then again the master fault and the ramp. And then again the master fault, and maybe this is more asymmetric. And then again you have the master fault and the rift, ramp. Why this is important? Because what the compaction syncline does when it's virgin the way I show you in Punta del Este, it accentuates the counter-regional dip of the four-way closures. You're adding by compaction, because you have the thickest part, the master fault is there. You add more and more overburden, and therefore what is critical, otherwise you're going to have a nice three-way that keeps coming up all the way to the continent, and it will create several main issue in the terms of trap geometry. So here is the same. You have the compaction syncline, you have the master fault. And imagine if you don't have that compaction syncline. Imagine that you have here, and then essentially this keeps going just around there. Let's say that the blue horizon, we just move it up and we put it here. There's no compaction. There's no compaction syncline, there's nothing. It keeps going. This high becomes a nice three-way because it closes toward the tips because it's a football trap. It closes toward the center of the basin, no problem there, but it keeps going and keeps going and going and going. Without a significant differential compaction, you will not have the four-way closure. So, what I think is really important, in addition to being the site where carbonates, obviously for the synrift with the cochineas, or the marine sag carbonates, this underlying reef shoulders they're very important. I think it's very important to realize first that you have virgins on both sides. There's no such a thing like, okay, virgin one way or virgin the other way. Secondly, I think differential compaction is providing the hanging wall compaction syncline over basement. I think that is very clear. And it makes all the traps, from the structural point of view, it makes all the traps where you don't have the master fault and the accompanying compaction syncline toward the continent, makes all those other traps much riskier from the structural point of view. In a way, a proof of that, is that when you take a look at the discoveries, rather in Angola or less recently in Brazil and the ones to come, is systematically, four-way closures, and we need to be careful about that concept. They may close, but as I said here, I think this is probably the most appealing. Imagine the same trap going to your internal, for those who work in companies, going to the risk committee, those ugly guys, and then you go and you keep going here, and they will say, well, I have a facies change, and then I have, shaling out. You go from you go from 0.8 on a structure to 0.4 out of the room or something like that. You're gone, And these features with PSTM are essentially very easy to identify. I show you a couple, but they're easy to identify. And they've been in the literature a long time ago, whether it's in Sirte Basin, in the North Sea, or in other places. I think by defining those, you clearly show that this, which is critical for all these traps, counter-regional dip, is there, and therefore your discovery will be here, whether in the SAG or in the rift carbonates, it doesn't matter. But essentially, this is the message I wanna pass to you. Look for this, because these guys are friends. Compaction synclines are friends. And thank you for your attention. The coquiness of the rift, normally they're just coquiness. When you go to the SAG carbonates, it's full of domal, domal lamellation that is clearly algal. Yeah. It's very common. One of the cores actually show that. We didn't have time to take a look at that. There was no reservoir actually in this particular case. The good news about Lobo, there are some good news, And how tough for the Uruguayans is to find source rock, The basement in offshore Brazil is volcanic. It's just basin. It's just basement. Here they found Permian. They found what? Permian. And for those who know, sedimentary rocks, Permian, not volcanic rocks, and probably similar to what is called White Hill in Africa, Irati, So the guys may have a source rock in the basement on which this is deposited. But as I said, partial analogs. This is not an analog for pre-salt 100%. I think there are some elements, but the reservoir was one of the issues. Yeah.
The direction landward and seaward.
I think it is. Yeah.
In terms of having a compaction positive feature.
Exactly. A compaction that enhances the counter-regional dip. Exactly.
And that would be in the siliciclastics rather than the SAG carbonate?
No, it's actually irrespective. It depends exclusively on the polarity and then overburden. The overburden takes care of the compaction syncline feature. And obviously it tapers toward where you have less displacement, towards the tip of the faults. Yeah. One way or another, these are football traps, And one of the issues that people need to be very careful when you map this is you have lateral coalescence of fault segments, and you have the bimodal, type of thing, displacement along the distance of along the stand of the fault, because what it's showing is that after the rift or even after the sag, those two segments are coalescing. Laterally, but the loci, where the reservoirs were developed, especially if they're carbonates, were in the original where you have for the individual segment you have the largest displacement. So you need to be careful, because you go a couple of contours down, and if you go in the very subtle saddle of those two, and maybe you end up with no reservoir. And you assume that is an entire ball high when actually it's not. It's just in that position that is
So you need to map the fault planes.
Yes, I didn't go into that, but actually at the end of the day, these are normal faults and applies all the good methodology of plotting the displacements and seeing if it's bimodal or unimodal will tell you actually if you are linking laterally two fault segments or not, or several. There are a couple of discoveries by Shell and Total that actually show that actually in Brazil.